Great. So welcome to the afternoon session. Very excited to hear about Brice talk about low-degree hardness for percent.
Hi. Thanks to the organizers for putting this week together. Today I'll be talking about some recent work on random KSAT, and all of this is joint work with my wonderful advisor, Guy. So in random KSAT, we sample a KCNF with M clauses by sampling all the literals IID and uniformly from n propositional variables and their negations. This is one of the oldest studied problems in average case computational complexity. The interesting regime of this problem is when the number of clauses scales linearly with the number of variables. So it makes sense to parameterize the problem by a clause density, m over n. And with this parameterization, we can immediately ask two natural questions. First, at what clause densities does a satisfying assignment exist? And second, at what clause densities can we find a satisfying assignment efficiently? We call these limits opt and alg. It turns out that opt is much larger than alg. So a third natural question is, what prevents efficient algorithms from succeeding beyond alg? And can we come up with some explanation of why algorithms fail beyond alg that generalizes to explain the alg values of other problems? Throughout, we work in the following double limit. We take k to be a large constant, the clause density alpha to be a function of k. And having fixed both parameters, we take n to infinity. In this limit, the value of opt is known exactly. It's this value here, as was confirmed by a paper of Ding, Lai, and Sun, and it's about 2 to the k log 2. But a lot less is known about alg. The current best algorithm that we know is fixed by Kojo-Oglan, which succeeds up to clause density about 2 to the k log k over k. This is almost a whole factor of k less than opt. So there's a very large information computation gap. Moreover, we have some heuristic structural evidence that this gap is inherent, and no algorithm should be able to beat alg. And this is because of a dramatic phase transition in the solution space of random KSAT around 2 to the k log k over k. Namely, below this threshold, the solution space looks like one large connected cluster, but above it, it looks like exponentially many small disconnected clusters. And in the shattered regime, local search heuristics are powerless. And that's some evidence that algorithms should fail. We will confirm this heuristic picture to a large extent. We show that due to shattering, the class of low-degree polynomial algorithms can't solve this problem at clause densities only a constant factor above that predicted value of alg. Low-degree polynomials are a computation class where all the output coordinates are polynomials of degree at most d in the inputs. We think of d as being about log n, hence low degree. We can input a KSAT instance into a low-degree polynomial by first encoding it as a vector of indicators. So we use a one-hot encoding where we allocate 2n indicators for the 2n possible values of each literal. And we feed this into a low-degree polynomial and get out a vector in r to the n, which we can interpret as an assignment by simply taking the sign. So think of positive as meaning true and negative as meaning false. And we say that a low-degree polynomial solves a random KSAT instance phi if this assignment that we get is approximately satisfying to phi. Here, approximate means two things at the same time. First, we're allowed to be wrong in a couple bits, so a small fraction of bits, and we're allowed to fix a small fraction of bits however we want. And second, that resulting assignment needs to satisfy most clauses of phi. So this is some relaxed notion of solve. And note that by relaxing the notion of solve, we make any hardness result against solving only stronger. We also require these two stability and normalization constraints on the low-degree polynomial. Are there any questions about this computation model?
Often that work in this model for lower density?
Yes. I'll show that on the next slide. So this computation class can simulate a lot of the best algorithms for random k-sat and for average case problems in general. Most notably, they can simulate fix. So the best polytime algorithm for random k-sat is a low-degree polynomial. Moreover, there's been an emergent understanding that for a lot of statistical problems, we think low-degree polynomials are as strong as the best polytime algorithms. And because of this, a negative result against low-degree polynomials is quite strong evidence that the problem is computationally intractable. We can now state our main result. We define this constant kappa star to be about 4.9. And our result is that if kappa is larger than kappa star, and we have a random k-sat instance at clause density kappa times the predicted value of alg, then no low-degree polynomial can solve this k-sat problem with with a large probability that depends on the degree. One limitation of our result is that we can only rule out algorithms succeeding with very large probability. But we do think that when algorithms succeed, they do succeed with quite large probability. Still, it would be nice to rule out algorithms succeeding at a lower probability, and we leave this as a direction for future research.
And what is the meaning of most clauses here? Is this with a fraction of clauses tending to 1?
A fraction of clauses that's constant in n, but dependent on k. So think like all but, I don't know, 3 to the minus k fraction of clauses. Did I see a question over here? Oh, no. Okay. This result is part of a long line of algorithmic lower bounds on random k-sat. So of these results, there's 2 that I want to highlight. First is the result of Gamarnik and Sudan against balanced sequential local algorithms on NAE k-sat. This uses a very nice argument, which is quite related to our techniques. And second is the paper by Hederick against survey propagation guided decimation, which you'll notice gets all the way down to the predicted value of alg. So that's the first result that gets all the way down to alg. Our contribution will be the first impossibility result against a class of algorithms that gets within a constant factor of what we think is the truth. And because this class contains fix, for the first time, we have a positive result and a negative result on the same class of algorithms with only a constant factor gap. We'll prove this result using the overlap gap property, which is one formalization of the clustering phenomenon. So the overlap gap property holds if in your solution space, any 2 solutions are either close or far. Think of close as meaning in the same cluster and far as meaning in different clusters. Recently, the overlap gap property has emerged as a general topological explanation of hardness. And for a lot of average case problems, there's been a lot of work, much of which is by people in this room, showing that the overlap gap property implies various classes of algorithms fail. Next, I'm going to outline the proof of our result. To introduce the ideas, we'll start with the Ensemble OGP, which is a simplification of our technique. This method originated in this line of papers. In the context of random k-sat, the Ensemble OGP will show that low-degree polynomials fail above this intermediate clause density, which is smaller than opt, but still far larger than alg. The argument goes, suppose that a low-degree polynomial solves random k-sat with quite high probability at this clause density. Then we construct this interpolation path of correlated k-sat instances, where the first k-sat instance is drawn from the k-sat distribution, and every subsequent k-sat instance is drawn by resampling one literal of its predecessor. So each of these phi's is marginally from the k-sat distribution, and the first and last are fully independent. And the middle ones are some mixture of the first and last. We run the algorithm on all the phis to get a sequence of assignments X. Our proof relies on the following structure not existing. The structure consists of two assignments, each satisfying some phi, not necessarily the same one. And that's where the term ensemble comes from, such that the two assignments are a medium distance from each other. And at this clause density that we needed, this overlap structure won't occur by the following first moment argument. We can plot 1/n log of the expectation of the number of pairs of satisfying assignments at each overlap. And if you look at the plot, at some point in the middle, it'll go negative. And at the overlap values where this expectation is negative, well, then that expectation is exponentially small. So that means that with high probability, this overlap structure won't exist. Given that, let's see how we complete the proof. So remember that if the algorithm existed, then every X will satisfy its phi with high probability. In this cartoon, I've drawn X0, and I've drawn as a red mote the set of assignments at medium distance for X0. I've also drawn the last assignment, XKM, which is far away, i.e. outside the mote, because the corresponding phis are independent, and independent k-set instances won't have satisfying assignments that are too close. Now, if we follow the sequence of x's, by the stability of low-degree polynomials, we only ever move by small jumps. That means we can't ever jump over the moat, but we eventually get to the other side. So at some point we land in the moat. And when we do, well, then X0 and that assignment both satisfy some phi, and by construction are at medium distance. This contradicts the OGP, so the algorithm cannot exist. Yes.
But X4 satisfies the fourth formula, not the 0th formula.
Yes, good point. That's why if we look at the forbidden structure, we require the assignments to satisfy some phi, not necessarily the same one. Any other questions? So this argument gets stuck at that intermediate clause density, because below it, that first moment argument that I showed no longer works. The graph doesn't go negative anymore. So to improve past the intermediate clause density, we're going to use the following enhancement, where instead of looking at a forbidden structure of two assignments at medium distance, we look at a forbidden structure involving several assignments. As intuition for why this should help, let's look at that plot at a clause density just above alg. You'll notice that the plot doesn't go negative anymore, but it still has a dip in the middle. And that means that if you look at the overlaps at that value, remember the y-axis is a log scale. So that means that the middle overlap forms an exponentially small minority. So it exists, but in some sense it's rare. And that inspires the following idea. If we consider a forbidden structure with a lot of medium overlaps, then hopefully we can boost this unlikelihood until we arrive at a first moment that's actually negative. And this is what we'll do. So this technique is called the Ensemble multi-OGP, and it originated in this very nice paper by Alex Huang. This argument will rule out low-degree polynomials at any clause density above the one we claimed. And the argument proceeds similarly. So we first we first proceed by contradiction, and the interpolation path is about the same as before, but instead of resampling all the literals once, after we get to the end, we go back to the beginning and do it again. a total of k times. So now any two phi's separated by at least km are fully independent, and all the phi's are still marginally from the k-side distribution. We run the algorithm on all the phi's and get out some assignments. We're going to need the following forbidden structure.
So can you explain how you got the interpolation path again? Can you re-explain how you got the interpolation path? I just didn't understand why things km are infinite.
Sure. So we resample the first literal from the k-sat distribution, and every subsequent literal every subsequent k-sat instance by resampling one literal of its predecessor. So after km steps, we're fully independent. Good question. We're going to need the following forbidden structure. To define this, we need a notion of multi-distance from one assignment to a collection of assignments. And I'm going to purposely keep this vague for now. Defining this properly will be one of our main innovations. So the forbidden structure consists of k assignments, each satisfying some phi, again, not necessarily the same one, such that the ith assignment has medium multi-distance to the set of its predecessors. And by some involved first moment argument, this structure will not exist. Let's take this for granted for now and see how we get the contradiction. So as before, with high probability, each x will satisfy its corresponding phi, assuming the algorithm exists. And now I've drawn x0 and a red mote of assignments at medium multi-distance, now from the singleton set x0. And again, xkm is outside this mote by independence. If we follow the x's, again, we only ever move by small jumps. Also, okay, sorry. We're going to construct this forbidden structure of y's one y at a time. So we'll always take y1 to be x0. And now we follow the x's. By stability of low-degree polynomials, we only ever move by small jumps. So we never jump over the moat, but we eventually get to the other side. So at some point we land in the moat. When we do, we call that assignment y2. Note that y2 is at medium distance from y1. And now we consider the new moat of assignments at medium multi-distance from the pair y1, y2, which is x0, x4. Again, if we look km steps ahead, we get an assignment that's outside the moat by independence. So now if we follow the x's by the same argument, we'll eventually land in the moat. We call that assignment y3, and so on and so forth. This procedure will construct a copy of the structure that was forbidden on the previous slide. And because of this contradiction, the algorithm A cannot exist. Excuse me. Of course, the key step in the previous proof, which I've so far glossed over, is how to define this forbidden structure, i.e., how do we pick the red motes so that the forbidden structure defined by them actually has an exponentially small first moment. And this is really hard. The only previous problem where this has been done is the paper by Alex Huang on Max independent set. And there, Alex uses this ingenious construction where the forbidden structure consists of some independent sets where the ith independent set has a medium non-intersection with the union of its predecessors. So this is the notion of medium multi-distance in Max independent set. Unfortunately, this construction is quite tailored to Max independent set because in Max independent set, the first moment that we have to control is essentially dominated by the number of distinct edges in the union of your independent sets. Whereas in random k-sat or in other problems, the corresponding first moment has much more complex dependencies. And it's a priori not clear how to pick the right forbidden structure for k-sat. And finding this generalization is our main contribution. So we identify the correct forbidden structure for random k-sat. And by an elaborate first moment argument, we show that this forbidden structure doesn't occur with high probability. Also, our forbidden structure is constructed from essentially generic energy considerations. And we believe that our methods can be generalized to show similar multi-OGPs for other average case problems. And if you remember from before, two-way OGPs tend to show algorithms fail at some point below opt, but still far above alg. Whereas many-way OGPs tend to show hardness quite close to, if not at alg. So if we can generalize this multi-OGP technique to average case problems in general, that could be a huge win for the community because it would show tight hardness quite close to alg for a lot of problems.
Do you know if you have the optimal analysis for your particular forbidden structure?
Within this, within this particular framework, at least, yes. There is a question of how to shave that constant factor of 4.911. We believe that it's not possible, at least with our techniques. We can.
Meaning there's like no similar structure, forbidden structure, or like this particular forbidden structure won't do it.
The particular chain forbidden structure that on 2 slides ago doesn't do it.
So for instance, it's not possible that this forbidden structure does do it, but first moment computations are not. Your analysis of this forbidden structure, like there's some threshold where this forbidden structure starts appearing, or this forbidden structure
Starts becoming forbidden.
Starts becoming forbidden, yeah. Do your analysis methods pin down that threshold precisely, or is it possible that your analysis is losing a constant factor from where this thing starts becoming forbidden?
Good question. So we showed the threshold for 4.911, and we showed that this analysis can't push beyond 1.7 something, and we didn't try to optimize this constant.
Okay.
Okay. In the rest of this talk, I'm going to describe how we define the forbidden structure. To define this, we need a notion of overlap profile. So for L assignments, their overlap profile summarizes all the ways that these assignments can agree or disagree. Formally, it's a vector of length 2 to the L minus 1, indexed by the unordered partitions of size 2 of the set 1 through L, where pi st is the fraction of coordinates where all the y's indexed by s agree and all the y's indexed by t agree. Note that unlike for independent set, where the forbidden structure only needed to care about the non-intersection of one set with the union of its predecessors, here we actually need to know all the ways that these assignments agree and disagree. And we can think of this pi as a probability distribution, because pi st is the probability that if you pick a random coordinate, then you get the agreement pattern st. And we can take the entropy of this probability distribution. We define this as the overlap entropy. In some sense, this measures the diversity of the set of assignments y1 through yl. And now we can define the forbidden structure as follows. We pick a constant beta star to be about 3.5. And our forbidden structure is, the first half of the definition is as before. And now we can fill in the medium multi-distance condition. We define the multi-distance of yi to the set of its predecessors as the overlap entropy of y1 through yi minus the overlap entropy of y1 through yi minus 1. So this is the additional diversity contributed by the coordinate, by the assignment yi. You can also think of this as a conditional entropy. And the medium multi-distance condition is that this multi-distance is about beta star log k over k. So this defines the forbidden structure at the heart of our multi-OGP. And our paper uses a first moment analysis to show that this doesn't occur with high probability. In summary, we generalized the ensemble multi-OGP, which was previously tailored to max independent set to random k-set. And we believe that our methodology can be adapted to other average case problems. For random k-set, we show that low degree polynomials don't solve it at a clause density that's a constant factor above the predicted value of alg. And I guess the takeaway is that many way OGPs can show algorithmic hardness at or just beyond alg. And I'm confident that this method can be used to attack many other problems as well. And with that, I suppose I segue into Mark's talk, which talks about tight algorithmic hardness for another problem using an even more evolved multi-way OGP. Thanks for your attention.
I'm sorry, I'm still missing something really basic. So you have this chain of assignments, and the ith one is allowed to, the only condition is that it satisfies one of the many formulas. So I still don't understand why it can't fall into the moat of the first formula, right? Or the moat of the, well, the moat around the first. Yeah, I'm sorry. I mean, what isn't the moat moving as we go along the chain, or can't it?
Yeah, that's a really good question. So I guess the
I'm not
idea
sure it's a
is
good
that,
question. You don't have to say that.
yeah.
That's a good question. Good thing.
The idea is like, like we have some like polynomially many clauses, or polynomially many case instances. And like really this, like you can think of this expectation as like a sum over like if you like case on which case instances are being satisfied. And like, you know, that gets you a poly factor in front. But all these failure probabilities are exponentially small. So like the fact that you have this ensemble only contributes like a poly factor, which gets swamped by the exponent. And it turns out that this like the probability of the failure of this, the probability of the forbidden structure occurring ends up being maximized when all the case instances are the same, because when they're different, you only get additional randomness, which makes things worse.
Sort of there's like super short answer to the repairs video if I said different words. It's just that the forbidden structure is something more complicated. It's not considering just a single formula. It's saying you can have y1 and y2 that satisfy any formulas. I don't care among the whole collection that overlap by this amount, and then generalize to many such solutions.
Okay.
And then by the reasons you said, the first moment calculation sort of doesn't care if you allow them to be solutions to anything within this collection.
So you're saying even if I define a new CSP, which is what you just said, satisfying means satisfying any one of these in the chain, that thing still has this overlap gap property in its solutions.
Exactly. Yeah.
Okay, I didn't catch that. Thanks.
A little bit of intuition for why your choice of forbidden structure ended up being the correct one. I guess it looked maybe complicated, but
well, if you look at like the expectation of the forbidden structure, you get a a combinatorial term corresponding to the number of ways, like number of potential copies of the forbidden structure, and you get a probability term of the the probability that some copy satisfies, and like these two terms have some trade-off, and by some analysis we can manage the trade-off of these and show that like when your overlap entropy is just this much, That's when the trade-off is the worst.
So this is informed by previous analysis, and you just the expectation with previous evidence structure. It doesn't work. So this choice of this entropy, right, is informed by the previous analysis of the previous forbidden structure that wouldn't give you the result that you want.
That's right.
Yeah.
Can I make a comment?
Yes, I did.
I don't know if you hear me. Yeah, I just wanted to say that I think this work, and to some extent previous work, highlights some interesting thing, that the hardness, if we believe the hardness is indeed occurs at 2 to the k over k, you can't really read this hardness from the associated Gibbs distribution, because if you look at the overlap distribution of randomly chosen assignments, the overlap is going to be trivial. So it's I guess what you would call it a replica symmetric regime, which is different from p-spin models where the overlap distribution is informative of the hardness. But in this case, I guess the problem is hard, even though the Gibbs distribution is trivialized. Not the Gibbs distribution, but the overlap associated with Gibbs distribution. So I guess the lesson, at least for me, is that you can't really read the hardness of the problem from the associated Gibbs distribution. Interesting.
Well, I think there's a partial answer to this, which is that if you look at the free energy, this expected number of things that are overlapping, there's that dip there. And so if you think about sort of like an average case version of OGP, then at least intuitively, there's exponentially fewer there, like Brice explained, and that's getting amplified by this construction. Andrea has
Also, you can see it from the Gibbs distribution if you look at point to set correlations, or if you look at distributions of pairs. I mean, the distribution of pairs is true, doesn't have two deltas, but it has if you look at the large deviation functions, it has a maximum, right? What's called the Parisi-Franz potential in physics. You pick one random solution, and then you look at the distribution of solutions at distance d from that random solution. And you look at large deviation function. That is a secondary maximum that appears. That is in case art, in p-spin, and that has been all along how physicists came out.
I couldn't catch half of that, so I'll leave it one day when I'm back.
So,